Welcome back. In the last video we looked at a nice property related to the determinant where we said the determinant is effectively linear, and now we're going to have some more properties to begin this video. So we can say that multiplying one row or column of a matrix A by a value k changes the determinant by a factor of k. So that was mostly in line with that first property we saw in the last video. So and then if we add a multiple of one row to another, that does not change the determinant. So again, I'm not adding a vector, I'm just doing row operations, really is what number 2 is saying. And well, number 3, if we swap two rows or columns, which is an elementary row operation, it changes the sign, so from positive to negative or vice versa. Okay, so the proof, I'm not going to go through the formal proof, but I'll just kind of outline the idea. We're going to use patterns to do this. Okay, so this would be a good thing to do in preparation for an exam or something like that. But the idea is that in each, you will have one of the following. So you'll either have an inversion, and then when you change it, it'll change to a non-inversion. And oh man, I can't spell inversion. And or you will have a non-inversion, and to begin with, really can't spell inversion, which will produce an inversion once you change it. Okay, so that's going to be the reason for the change, particularly in number 3. Okay, so now just kind of using these properties, okay, we want to show that this determinant is 2 through elimination. So yes, you can use cofactors, yes, you can use patterns, but we're not going to do that. So if I do elimination, so that's the idea of row operations, I'm going to say start with looking at 1, 1, 1, 2, 3, 4, 4, 9, 16, and then through elimination I'm going to eliminate the first or the second and third entries in the first column, and so when I do that I would end up getting 1, 2, 5, and 12, and then I can continue to eliminate using row operations, 0, 1, 2, and then if I fully reduce it, be 0, 0, 2, and then we know that from last week the determinant is of an upper triangular matrix is just the product of its diagonal elements, so then that enables me to say, oh, the determinant is just 2. Okay, so if you didn't want to do cofactors, you could do elimination. Okay, so I want you to try this one on your own, and so pause video, try it out. And so here's my solution. You can kind of see my work and follow it through. I got 8 at the very end using elimination. You could do a different sequence of steps and get the same thing. Now, some other handy properties. So in addition to thinking about how row operations change the determinant, some more properties is that if we have the determinant of a matrix product, we can do the determinant of each matrix, or determinant of each matrix, and multiply those products or those determinants together. If we have an exponent on a determinant, same as determinant, and then of the matrix, and then to that exponent. And then if it's invertible, the determinant of the inverse matrix is 1 over the determinant of the matrix that isn't inverted. Okay, and then lastly, remember we talked about similar matrices a while ago, and that just means that we have some way of connecting these two matrices together with change of coordinates, s, so we're changing from one basis to another. So if we have the determinant of A, or so if we know A is similar to B, then their determinants are going to be the same. Okay, so this was really wrapping up 6.2, where we were looking at all the algebraic properties of the determinant. Now, in the next video series, next few videos, we're going to look at the geometry related to determinants.